Okay, let's look at our first example from this 2.6 homework, going over differentials specifically. And this is number 6. So this one asks us to find delta y and f prime of x times delta x. And I like this one because these are two different values. Delta y represents the exact change in your y values. How exactly did y change when I changed x? But f prime of x times delta x, remember, is just my way to approximate that value. It's not going to be the same because it's just an approximation using the derivative. So let's start with delta y. Delta y, of course, I can find by doing y2 minus y1, or since this is in function notation, I can write it like that, f of x2 minus f of x1. But what are x1 and x2? Notice what it gives me. This function gives me an x value, only one x value. It only gives me one x value, and it gives me a change in x. So this x value right here represents my starting value. My starting x value, meaning that, yes, this is my x1. So your starting x value represents your x1. So how do I find x2? Well, to find x2, you can just take that starting value and add whatever your delta x is. So in our case, it's just negative 1.7 plus 0.1, and I get negative 1.6. Okay, so now that I have both of those x values, I can now just do my function value at my x2, which was negative 1.6, minus the function value at x1, which was negative 1.7. The function is just 8 over x to the fourth, so I get 8 over negative 1.6 to the fourth, minus 8 over negative 1.7 to the fourth. Now this problem does say to wait to round until you get to the end and then round to 4 decimal places, so I'm going to try and do that here. I get 1.220733125 minus 0.9578429. When I subtract those two things, I get 0.26286018729. But at this point, all my computation is done, and so now I can go ahead and round to 4 decimal places, so I get 0.2629. So that's my actual change in y as I let x change by 0.1. But now let's approximate it. Let's approximate it using the derivative. So delta y can be approximated by doing the derivative times delta x. And specifically the derivative at my starting spot. So when I say x in here, what I'm actually talking about is x1. So with that in mind, in order to do this, I need the derivative of my function. So f of x is equal to 8 over x to the fourth, or 8 times x to the negative 4, since it's in the denominator. When I take the derivative of this, I get negative 32 x to the negative fifth, or negative 32 over x to the fifth. So now that I have that, now that I have my derivative, I get negative 32 over what's my x1? My x1 is my starting x value. So negative 1.7 raised to the 5th power times my delta x, which in our case is 0.1. When I throw that into my calculator, I get 2.253748 multiplied by 0.1. Multiplying by 0.1, all that's going to do is just going to move my decimal place over, so I get 0.2253748. And now I can go ahead and round to 4 decimal places, and I get 0.2254. So notice how close these two numbers are. They're not exactly the same because, once again, the second number is just an approximation, but they're close because delta x was relatively small. The top one is the exact value, and the bottom one is the approximate value. And like we said earlier, the reason for this is to save us some computation. Notice how in my actual computation, I had to raise this decimal to the 4th power twice, here and here. But in my approximation, I only had to do it once, making that computation a little bit more simple. Okay, let's look at another example. And this is number 7, so the very next problem. And this is a really cool example because this shows how computers can use this to approximate irrational numbers. When you plug in something like this, the cube root of 7.57, the calculator's not actually giving you the exact value, because irrational numbers, you can't find the exact value. They're non-repeating decimals that go on forever. So what the calculator's doing is the calculator's using different processes to approximate it to a specific degree. And that's what we're going to do here in this example. We're going to just approximate this value using this idea of differentials. So take a look at this, cube root of 7.57. I don't know the cube root of 7.57. 7.57 is not a perfect cube, but is there a perfect cube close to this that we do know? Well, we do know the cube root of 8 is 2. So I can use that to help me approximate that by declaring I'm going to go ahead and let x1 equal 8. Why am I choosing x1 to equal 8? Well, in order to make sense of that choice, we also need to understand what the function is. Because remember, in order to use this method, I need a function. What's my function in this case? What am I doing to this number? I'm taking the cube root. So my function is just this cube root of x. And I'm going to choose 8 as my starting point because that's a really easy number to calculate the cube root of. It's a perfect cube. But I'm trying to approximate 7.57, which is not 8. It's close to 8, but it's not 8, leading to my third piece of information that we can find. What is delta x? How much did I tweak my x value for this approximation? How much am I changing the x value? Well, if 8 is my starting point, that means I'm going backwards 0.43. And if you want to check this, just realize that 7.57 is equal to 8 plus negative 0.43, and you get 7.57. So here's your x2, here's your x1, and there's your delta x, from what we just saw in the previous example. So I now have my starting x value. I now have my function, and I now have my delta x. And so I am now ready to approximate the change in y using this formula. Well, in order to use the formula, once again, I need the derivative of my function. So if f of x is equal to the square, or the cube root of x, that's the same thing as x to the 1/3. And therefore the derivative is equal to 1/3 x to the negative 2/3. So I get delta y is approximately 1/3 x to the negative 2/3 times delta x. Well, now we're ready to go. Because now, what am I going to plug into my derivative? I'm going to plug in my starting x value, which is 8. What is 8 to the negative 2/3? Meanwhile, delta x, we already know, is negative 0.43. Well, if you plug 8 to the negative 2/3 into your calculator, you're going to get 1/4. And the reason why that's such a clean number is, once again, because 8 is a perfect cube, which means 8 to the negative 2/3 is also a rational number. So this leaves me with negative 0.43 over 12, which if I put that in my calculator, I get negative 0.03583 repeating. So using this concept of differentials, we now were able to approximate the change in y based off what I declared my function as, a starting x value and a change in x. So is this my final answer? No, this is not your final answer. We shouldn't be getting a negative if we're cube rooting a positive number. So how does this help me find my approximation for the cube root of 7.57? Well, in order to understand this, we need to kind of understand our notation a little bit more. We know what my function is. Function is cube root of x. We know what x1 is. We picked 8 because it was a perfect cube as my starting point. And we know what delta x is because that gave me my x2. 7.57 represented my x2. So this right here is really f of x2. That's what we're trying to figure out. We're trying to figure out my approximation for f of x2, the cube root at my new x value. But what did we just find? find? We found my approximation for delta y. And remember that delta y represents the change in your y values, or f of x2 minus f of x1. And like we said earlier, f of x2 is that cube root of 7.57. What's f of x1? F of x1 is the cube root of, what did we choose as my x1? The cube root of 8. So with that in mind, cube root of 8 is just equal to 2. And so I get negative 0.3583 repeated is approximately the cube root of 7.57 minus cube root of 8 is just 2. And from here, I can solve for that approximation by just adding 2 to both sides. And I'm left with the cube root of 7.57 is approximately 1.964. I'm rounding to 3 decimal places because that's what it asks you to do in the problem. And that's my approximation of what the cube root of 7.57 is. Okay, good luck with the rest of the problems on the homework. If you have any questions, feel free to reach out, and I'll see you in the next video.